So we are glad to have Lev Glebsky, who will talk to us from Mexico on equations over groups and approximation of groups. The stage is yours, Lev.
Okay, thank you very much. So no, it's something, let me put it here. So I will speak about equation and approximation of groups and start with Sophie groups. If who attended seminars talks before, was several good how to say descriptions of Sophie group, geometrical description. And I'm planning to give some more algebraic or maybe even like model theoretical description. Yes, so and we start with Hamming distance. I remind that Hamming distance, recall you that Hamming distance is just the normalized number of points where for permutation, that permutation do not fixed. So it's normalized support of the permutation. And using this Hamming distance, I could define what means Sophie group in the following sense, in the following how to say, by the following. If my group I represent as a free group, as a quotient of free group by a normal group, then I could define the Sophie group as follows. So for any finite set of subset of the free group, and for any number, small number, I could find the homomorphism from a free group to symmetric group, which separate my normal subgroup from other elements. And the separation means the following: if my words is in normal group, I mean in this finite set and normal group, then this image is small, and if not, then image is large. So it is basically the same definition. It's easy to check that it is equivalent to the definition of Sophie groups. Okay. So, and from here, it's easy to see that if group is Sophic, then it could be embeddable in the quotient of product of symmetric groups. It is rather standard. It's related with so-called universal Sophic groups by Ehrlich and Szabo. And it's not difficult to understand why it should be. So I just take these finite sets that cover all my free group, take this epsilon which goes to 0. For all this, I could find this morphism. This morphism will define morphism of free group to symmetric group. And then I just how to say, I just take off errors. So I just take a quotient by subgroups, which is defined by errors. And this subgroup, how to say, it is normal subgroup just because this normalized Hamming distance is B invariant. So it doesn't depend on conjugacy. It's the same for elements of conjugacy class. Okay, it's a little bit, I think, less known that the other direction is also true. So if the group is subgroup of a quotient of direct product of symmetric group, then it is Sophic. So it's let me state it is the same as to say that the quotient of product of symmetric group is Sophic for any normal subgroup. Okay. Let me just sketch how it is possible to show. So how it is possible to show. what I need is the compactness of direct product. Also, I need the following property of Hamming distance. Is basically what is written here is written that if I have some permutation, which is okay. Now instead of symmetric group, I want to consider alternating group because it's okay. It is not too much difference between symmetric group and alternating group. I mean. Okay. What is said here that if I take an element, then it take its conjugacy class, then its power cover. This is neighborhood of identity in this metric. So it means that power of conjugacy classes cover as much as possible. This 16 doesn't matter. What it matters that it is independent of K and P.
I'm not sure. Let me just make sure that I understand what you mean. You mean that every element of norm at most K times the norm of P is a product of a constant K times conjugates of P.
Yes. It is exactly the same. This is actually, you see, there is a work of okay, it's the same is true for any finite prime not exactly the same for any finite simple group that the product of conjugacy classes is grows as fast as possible. I mean, with constant factor, but it's said a little bit more because if I restrict on support of P, then permutation of support is just four times. I need just 4 times permutation to cover all permutation with given support. But then I have to, how to say, to spread my support as large as I need. So it's also I could do by conjugation. So what is written here? Okay. And the last ingredient, what I need is what is called amplification trick. It's allow me to increase the Hamming norm of a permutation. Just take this permutation and consider. Okay, it could be the same. P could be the same and consider as permutation of pairs, and then happens that the Hamming distance is growth. So okay, let me explain how I could prove it. So first, suppose that I have X and Y. Which is in this product, and let me write alternating group instead of permutation, and such that X is in M and Y is not in M. Y is not in M. Okay. Then of course Y is not in the product of okay. Let me denote this as D. Y is not in the product of conjugacy class for any D. Then by compactness, it follows that for some projection on some element is not true this. For some projection, it is not the case. And then by this property, by property 2, it follows that this distance is small. Yes, this distance is small. And then using amplification trick, I need that this is, I could increase the Hamming distance of y. So I could increase the Hamming distance of y, take it more than 1/2, still having this fraction small. So this actually how this proof works. And let me just note that this proof does not work for hyperlinear groups. So, and the reason is that exactly the property 2 is not hold for this metric which we use for hyperlinear groups. But for example, it works for if I consider projective PSL groups over some finite field with rank metrics. Everything works the same. So it's also true for this case. So I just want to say that it is not true for any. I mean, maybe true, but it is not. So it is not. The proof used some property of metrics and groups. Yes, it is not very general. I mean, not.
But Lev, I don't think I understood. What is the definition of P? The few lines before P cross Q.
Where?
This 5 lines before.
Okay, I have permutation on n elements of permutation of m elements. P cross Q is just permutation of on pairs. So
just on the pairs. Okay.
Yes, I just consider P cross Q as action on some pair.
Okay,
Just so P on Y and Q on J. So, and it's easy to contain how fixed point has this permutation if I know fixed point here. I mean, it's easy calculation. And this allows me to increase the norm of Hamming norm of the permutation. Still keeping quotient, still keeping fraction small. It's clear now. I don't know. Maybe there is questions, and because I could.
But yeah, but why this proves the theorem? I don't see it.
No, it is not. I mean, it is not. It is not. You see, I have to separate x and y if x is an m and y is not in m. And this actually what I'm doing. I separate in the sense of the definition in the sense of the definition of this definition.
I see.
And what I'm doing, I take some x and y and try to separate them. Okay, the proof is a little bit, there is some more details because I have to separate sets, not only finite sets, not only pair.
Mm-hmm.
But it's basically the same.
So basically, okay, you say that if I understand, you have to separate elements with large support from those with small support, and then you say by this amplification you can make it as small as you want.
The main difficulty here is that support of both may be small, but support of one is much smaller. But I could avoid this using this simplification trick.
I see.
This what?
Now, property 2 for the symmetric group is elementary. For the other simple group, it's not so easy.
Yes.
For the symmetric group, I guess it's easy.
First, for symmetric group is not true. For alternating group, because this is why I change symmetric by.
Oh, I see. Okay, I understand. Okay.
Yes. Yes. And yes, there is a proof. I mean, just direct proof. You play this permutation and multiply them.
Now, what about UN with the Frobenius norm instead of the hyperlinear? Then it may be true, not?
No, it is not true, because you see, take for example, n is very large. We could take this Hilbert-Schmidt norm could be small for two reasons. Because, for example, because its norm is very small, or I mean this distance could have a small rank, for example. Then if I have a large power and of A, but not too large, then it still will have small rank and not cover all.
No, I'm not talking about rank. I'm talking about the Frobenius norm.
Yes, but Frobenius norm could, you speak about, not for Hilbert-Schmidt norm, for Frobenius norm.
Yeah, for example, or operator norm, or any.
Okay, I don't, yes, I'm not sure. I don't know.
Because the hyperlinear is maybe the problem that they are not kind of compatible. You know, if you put it inside the bigger one, the normalization is different. On the other end, the norm, the other norms, like, you know, the P norm or the operator norm, if you embed, you know, UN inside UN plus 1, I think the norm is preserved. So maybe there is a chance that this will work over there.
Okay, it might be, but probably 3 is not working here. I mean, because amplification is works for rank, for counting this, but probably for normal norm,
I see.
It could be, yes, but yes, I understand your question, but I'm not. I think it requires some thinking. Okay, so let me go. Okay, so now I want to reformulate. I want to reformulate these things. So the group is Sophic if and only if it is embeddable in the quotient of direct product of symmetric group. Okay, I could reformulate it using equations of a group, and first let me explain what I understand by equation. What I understand by equation, it's something. Okay. So first I should fix some set of symbols for constant and set of symbols for variables. And in this language, equation is just element of a free group generated by these two sets. I just want to distinguish between constant and variables. Okay. Some example is this that one element is equal to the other element, conjugation of the other element, or I could write it as in definition as a one word. And here, this is supposed to be constant and this is supposed to be variable. So then what I say that equation is solvable in a group, it means that this sentence is true. So for any election of constant, I could find a variable. So it's I think it is natural definition what it means, solution of equation. And I say that equation is solvable over group if for any election of constant I could find a solution, but in larger group. So it is so I could find a group which is larger. Okay, but basically it's easy to understand what it means. What it means that this equation is solvable. It means that, okay, of course I could take J multiplied by free multiplied by free group generated by variables, and take quotient by normal subgroup generated by this element. Yes, and then it's easy. What means that I could solve? It means that that I not borrow elements of J. So J is embeddable here. So it's instead of write like this, I could say that in this way.
Injects into this.
Yes, injects. Yes, injects. Okay. Yes, it is. Okay, let me clear this. Okay. So the statement is that the group is Sophic if and only if every equation solvable in every symmetric group is solvable over Z. It's actually how to say? It's actually rather easy follows from this characterization, because okay, in one direction it's almost trivial because this is solvable. Yes, my equation solvable here. Okay, if I take quotient, it will be solvable in here. I mean, because quotient don't change solvable in. So, and this J is included in this thing. So it's if it is Sophic, then every equation is solvable over there. And other direction, I could. It's also not so difficult. I could. What I can do, I can. Okay, let me say. I can my free group. I can embed in the product of symmetric group, but embed in such a way that I take all possible gamma-morphism on all possible symmetric group. Then it's a kind of universal embedding. Yes. Then if my group J is F by N, then it should be, if it is Sophic, it should be embeddable in this. So I take normal subgroup here and generate normal subgroup of this group. Then group is Sophic if this is actually embedding. Yes, because if this map is actually embedding. And okay, if not, it means that exists some element of a free group which is not in N, and elements of some elements of in N, such that this element is in this normal subgroup. Yes, and I could just write what it means. X1, X2, and so on. So it is exactly an equation which is not solvable in this group. Okay, over this group. It is exactly equation which is not solvable over this group. Okay. So it is, there is questions up to here. Everything is clear.
This is somewhat interesting because it maybe suggests that what I suggested before cannot be true, because you see here you get a characterization of being Sophic using the symmetric group as quotients of the product of the symmetric group divided by some normal subgroup, but the normal subgroup has nothing to do with the metric on the symmetric group. It's just a purely algebraic.
Yes.
I wanted to suggest something like that over UN, which depends on the metric, and if it would be true, then it would mean that the group will be Frobenius approximation if and only if it is operator approximation, if and only if it and we believe, we don't know counterexample, but we believe that it's not the case.
Yes, I see.
I see.
Yes,
okay,
probably it would be very strong. Yes. What? Okay. So let me go. Okay. As far as I know, this characterization of Sophie group by equation is not so useful. I don't know how to use it because it's very difficult to understand which equation is solvable. I mean, in every symmetry group. But if we speak about other approximation and approximation, for example, we could try to define the same thing as Sophie group and ask for approximation by all finite group or all finite solvable group or all finite nilpotent groups and define a kind of approximation. And maybe it's easy to define it like this, that just using what I'm speaking before, that a group is approximable by some groups of this class, if and only if every equation which is solvable in this group is solvable over this group. I just okay, and it's one can see that, for example, groups approximable by finite groups by this definition is exactly weakly Sophie groups.
I don't understand. Now number one is a definition.
Okay, I see. I could define it in different way, and because you see, because normally we could start as Sophie group, but now take any metric. If we take any B-invariant metric, it's boiled down that it is if and only if it is a quotient of direct product of elements from here, or here. Because now I don't have to do these tricks about amplification and anything like this, because I take any metric.
What do you mean any metric? So you define approximation with respect to some metric? Because
if exists, I define fin approximable if exists a metric, B-invariant metric, such that happens something like in definition.
If there exists some metric, okay.
Yes, the same for solvable and the same for nilpotent. Then it's more easy because now I have a choice of a metric. I could elect metric as I want to prove that it is the same as to be a subquotient of direct product.
Yeah.
And this is the same as to be solvable over groups. Okay, so but yes, in general the definition is by approximation and on this, but it is equivalent. I mean, for these classes, it is exactly equivalent. So I could use it as a definition. Yes, I think. But it is not a standard definition. Well, say this. Just okay. Okay.
So number two is just a name, right? You say if it's approximated by some finite group with some metric, then you call it weakly Sophie, right? That's a name, just.
Yes, some finite groups with metrics. Yes, I mean all finite groups, because my class approximation is class, depend on the class. So I have to take all finite groups and define and each of them metrics. And if I could approximate it, then it is weakly Sophie. Okay, but it is boiled down.
Say, so for Sn, you just proved that you can consider only the Hamming matrix. Yes.
Yes. This exactly. In some sense, Hamming metric is a universal metric. It's the metric of the best approximation. And yes, it's but in alternating group, it is the only metric. in some sense, because of this result of Shalev and okay. So what? Okay, let me go. Okay, and now I want to speak about some application of this characterization by equation, and all this application is about weakly Sophic group, so it is not work for. Okay, let the first statement: if a group is approximable by algebraic groups over algebraically closed field, then this group is weakly Sophic. Okay, so it's for example, I could take some matrix group, yes, over some algebraically closed field, and consider, for example, rank metric in this group and approximate my group. Then this group will be weakly Sophic. Okay, so the proof is like this. First, if this group is approximable, then it is embeddable in the direct product of, in the quotient of direct product of algebraic group. This Hj are algebraic group, and then it's everything boiled down that we have to show that if equation is solvable in any finite group, then it is solvable in algebraic group. Yes, because then it will be solvable here. It means that solvable over here. So it's what we have to show. Okay. How we could do it? Suppose that we have algebraic group of an algebraically closed field and some equation which is not solvable here. Then it is not solvable in some finite group, and we just could construct this finite group where it is not solvable, and this is not difficult. This group is basically the same algebraic group but over finite field. So what we do is we take group equation. We could it boil down to algebraic equation or system of algebraic equations, and here also I suppose that define an equation of a group. Then if this algebraic equation has no solution, it means that ideal generated by this is everything. It means because of it's algebraically closed, that it means that I could write like this, and I could find some polynomials which generate this one. Then I could consider ring which consists of generated by all coefficients of these polynomials, and take quotient of this ring, and which is field, and this quotient is a finite field by that. I mean, finitely generated fields as a ring is finite. Yes, this what happens, and this will be a group where already my equation has no solution. So this what happens for approximation by algebraic groups over algebraically closed fields. This is not true, say, for example, for unitary matrices. So it is not true. This statement is not true for hyperlinear groups. So I mean not statement. Okay. This statement. Statement one is not true, and I could just find the equation like this. So if I take, you see the reason why this equation is not solvable in unitary group is clear, because if if J is small, I take this commutator, which also small, but I can take a large power which make me element is large. I mean close to 1. Small is close to 1. This will be far away from a 1, but this, because M should be supposed to be smaller than, I mean, M is something fixed and smaller than this number. Then I am not just able to grow to go far away from the 1 using this multiplication. And this is true, and this is solvable in any finite group by results of Nikolov and Segal, which say that any commutator is the product of fixed finite number of
bounded number of depending on the
yes, a commutator, every element in commutator group is bounded number, and this bound depends only number of generator. And this M basically here the number of generated I need is just 2, because I just J and F. So so this, I mean, it's essentially used that this group is over algebraically closed field. It is not true for. Okay.
So but there's something stranger. So you say that UN as the so it means that UN as a group is not weakly. Sophic.
No. It is not say this. It does not say this. It says that this because weakly Sophic is over, but here it says that in.
I see.
So it's always.
I see. There is an equation which is solvable over a finite group, but not over UN, but it might be solvable over a bigger group. And I guess it must be, because finitely generated groups are residually finite, so I guess they are.
Yes. But not solvable in. This is so it is always play with over and in. So it is not solvable in. So here everything is about in and over. Okay, maybe there is other questions.
Just to make sure I understand, your last comment is to say that you did not prove that hyperlinear groups are weakly Sophic?
Yes. The statement 1 is not true, yes. But it is not, I am not able to say that hyperlinear group is not weakly Sophic. It is an open question. Yes, I am not able to prove just this. Yes, we stop in these algebraic groups, and then I'd like to show another application. This is the following statement. If he says that extensions of residually finite groups by weakly Sophic groups is weakly Sophic. So it says that if n is weakly Sophic and this is residually finite, then K is weakly Sophic. So extension, I don't know extension of which by which, extension of residually finite by weakly Sophic is weakly Sophic or.
Okay, I just tell the people that's exactly what I told you about. In fact, it's much stronger than what I told you. In the case I was interested, it is an extension of a residually finite by a finite group, and a finite group is certainly weakly Sophic. So this theorem is going to include what I told you before. Okay, thank you, Lev.
But no, it is not about Sophic groups. So it is about just
weakly Sophic, yes.
Weakly Sophic group, yes. Right. And for Sophic group, what is proved that if it is Sophic and this is amiable, then it is Sophic. So it is a bit stronger, but not for Sophic group. Yes, not for. I mean, not stronger. It's different. Yes, it's in some sense.
Yeah. But what is important for me, you know that I just say that this group of the Lin is covered by this theorem, but it's not covered by the theorem which implies that an extension is Sophic, because then it should be amenable by Sophic.
Yes, extension, this is residually finite and this residually finite. So it should be weakly Sophic because residually finite is weakly Sophic.
Right.
Okay, so let me the main ingredient of the proof is to prove the following. If I have some finitely generated residually finite group, I forget to write here. Here should be let me. Yes, should be finitely generated residually finite here. This is residually finite group, and H is finite group. What happens? And H is finite group, and if I have some equation which is solvable in every finite group, then this equation is solvable over this wreath product. The wreath product is okay. Should I remind what it means? It is a semi-direct product of a group of functions with of functions from J to H with natural action. Yes, just shift natural action of J on these functions. Okay, so what I want to show first is that that every equation solvable over in every finite group solvable over this group. So let me okay. Entonces, so if so I take some elements of this group which I write as a product. Not elements, because it is a tuple of elements, which is a product of f and function and element of the group, and I want to find the solution. And where I will find the solution? I will find solution in this wreath product, where this group, I think it is written, where this group is profinite closure of this residually finite group. And how is to say this what I want to say. Profinite closure. Okay, and so the solution will be here, and it's easy to see that I could embed this group to this group just okay, because this is profinite closure and this is residually finite. So J is embed to J hat, and functions, I just take a functions if for functions which is on element which is not in J, just to put it 1. So then this defined an inclusion of this group to this group. So it's actually extension of not extension. I mean this includes this group. Okay. So how I can find this solution? The main trick here is that if I have semi-direct product, then equation is also like semi-direct. So I have to solve it on this, just on this component, and then lift it to other component. But the situation that I solve it in the first component, but just not solve. I want to find a solution which is universal in some sense, and this solution is like this. What I want to say that Y is universal solution if for any finite quotients, if I consider its infinite quotients of my profinite group, then for any functions, from any function in these quotients, I could find the functions which give me a solution. This is already in a finite group. Okay, this is possible. This is possible because, because in some sense, if I have a functions, everything is finite. And I could make all possible functions, I mean, in one things and find this universal.
What the connection between M and K?
No, it's just number K is just number of constant, and M is number of variables in my equation. So what is written here is that okay.
I see. So it's really okay.
It really doesn't matter. I just say that this not just one not just one A and function. It's just quadruple of A and functions, because I could have several constant and several variables.
So this is for every M it should hold.
I fixed my equation. If I fixed my equation, I fixed K and M. Yes, because K is number of constant and
I see.
Number of.
Sorry.
So it's okay. So the first statement that these universal solutions do exist, and then we may consider finitely generated subgroup, which generated by my constant, yes, which and by this universal solution. And now the trick to find solution here is playing in different topology. So we could find continuous function in profinite topology such that this function is continuous. So it means, basically it means that it depends on some finite quotients here, because H is finite group. And but these functions is is convergent to my function f, initial function, in direct product topology if I consider them as a function on the group generated by A and Y. Yes, I just restrict my function on N and on subgroup generated by A and Y. This is already finitely generated group. Its Cayley graph is a good thing, so we could define product topology, and I could find this function which converges in this topology. And okay, for these functions, because this continuous, and because my Y is universal solution, I could find also solutions such of this equation. And then I just, because I restrict this function on this subgroup generated by this finite set of elements, and because this is compact in product topology, I could find limiting point, and this limiting point is exactly solution of my equation, of my initial equation of my equation. So it's some how to say this explanation of the proof is plain with two topology: profinite topology, which is used to find universal solution, and then I find these sequences of solutions, and then I restrict my group just on subgroup generated by two elements by these finite sets, and then consider direct product topology. And so actually solution is not...
Lev, may I bother you for a second, because there's something not clear to me. the group you started with a group which is extension of G by finite group. You embed it into such wreath product.
Okay,
now, this wreath product is not residually finite. Otherwise, the original group will be residually finite, and there is nothing to prove.
Okay, I am not speaking about this statement. I am speaking just about this statement. Okay.
What?
I am speaking about that any equation which is solvable in.
Understand? No, I understand. Okay. But somehow okay. I don't understand where is the magic suddenly, because this is not residually finite.
The magic is that this group. Oops, what happens? The magic is that this function is not supposed to be continuous in profinite topology. Okay, and these functions also. Okay, these functions are continuous in profinite topology, but I consider now limit with respect other topology.
I see.
Okay? So, and this is the same limiting point with respect to other topology. This group is not continuous in profinite. I mean, this function is not continuous in profinite topology. So here the wreath product is not topological wreath product. It's abstract wreath product.
I see. So it's an abstract wreath product. So it's not residually finite. Your group is embedded, and you find a solution inside that group.
Yes, and actually I don't need whole this stuff. I just need subgroup generated by this A and universal solution. Yes. This what happens, and this actually the trick is here that first I find universal solution playing just with this second component of these elements. Yes, this is as profinite things. And then actually, okay, I approximate my functions by profinite things, but consider limit only in this group, already in direct product topology. Okay. So yes, it's like this. Okay, now how from here I could from this I could prove this statement, and is okay. Let me so first my group K, this is well known, is embeddable in wreath product. Okay, so it's because this is weakly sophic, it means that N is embeddable in this product of finite group, quotient of finite group. Okay. So, and this wreath product is embeddable here and embeddable here. And now I want to find solution of this equation here. Okay. What I do? I could take a pre-image of this without quotient. Okay, then I could find a solution. Yes, in this it's just because just by component. Yes, and then I could take quotient, and it will be my solution will be in this quotient because I am not, because you see what trick is here, that extension is by this part. Yes, but quotient I take only this part. It means that this group is embeddable here. So I am not borrow this embedding by taking this quotient. I mean this what happens. So I am not. So and this actually how the proof works. Okay, it's probably what I I was planning to talk today.
Mm-hmm. Yeah, okay, so very nice. Okay, so I just, when you were not with us, I made a preparation saying that this group, these results will show that the group that we will meet in the next 2 weeks, this constructed by technique of the lean, which is not residually finite and not for values approximated, it is still weakly sophic, yes, which makes it even more mysterious if it's sophic or not.
Yes, and I believe that this technique is not, I mean, as far as I understand, is not so easy to adapt for sophic groups, maybe even impossible, because you see what is used here, that if that semi-direct product of finite group is finite, and so I could find a solution in this semi-direct product, keeping this structure. Then about sophic group, then yes, I have find solution, but in some permutation group which contain this, and I lose the structure of this semi-direct product. So it's and everything break down here. So it's not.
Okay. Any more questions?
Yeah, so just about this last thing that you said, if you think that the only obstacle is, do you think that the only obstacle is this fact of semi-direct products? Like, for example, you could apply this to the other classes of finite groups that you mentioned, starting with solve, nil, and...
Yes, it is possible, but yes, I think yes.
So for solvable, it should work, right? Semi-direct product of solvables is solvable.
It should work. You see, solvable for solvable and nilpotent approximable group, it is proved that not all groups are approximable by solvable and nilpotent. Yes,
okay.
It is there is such a result, but there is no result for weakly sophic groups. So maybe that's why I think it's more interesting.
Okay, thanks.
Okay. Some more questions? Okay, I don't see you, so if you want to say, just talk, and if there is no question, so let's thank